Hey everyone. So this time we're going to be talking about composition, what the object is made out of. And we can figure that out by looking at the different types of spectra. And we're going to talk about the three types of spectra. You've already dealt with one of them. The continuous spectrum is that curve, that rainbow that we used when we were finding Wien's law, the temperature, when we were finding Stefan Boltzmann law, the size, things like that. So today we're going to introduce the other two types from there. But this method for finding the composition, what the object is made out of, works for stars, but it works for everything else. It works for planets, it works for galaxies, it works for nebula, it even works for substances that we have here on Earth. So once you've learned how to identify the fingerprint of a particular element from its spectrum, you can figure out what's there. So let's get started. So as always, have your class notes out. Tool 12, finding composition, looks like this. It would also be a good idea to have your practice out, because on the back side of the practice sheet is a reference library of spectra. This is what you're going to be using for identifying substances. So you're going to want to have this out, and then you're going to be using it throughout the semester for this. So you're always going to keep this handy whenever we're working with this. So go ahead and pause the video, go ahead and get both of those out so that you're ready to go. Okay. So we've talked about how we get information from light. We've talked about how to find the temperature. We've talked about how to find the size. And today we're going to talk about how to find the composition, what it's made out of. Composition is what that substance is. We've talked about the continuous spectrum already. That's when I've got a hot, dense, glowing object, shines through the prism, and it makes that rainbow. But then you remember that we often will use this type of spectrum, this line spectrum, so that I can determine, exactly how much of these different colors that we have. And then the peak color then here will give us the temperature. If I know that plus the luminosity, then I can get the size of the object. So before I can introduce the next two types of spectra, we need to kind of review atomic structure here just a little bit. And if you've had any of this in chemistry, this is all going to be completely familiar to you. But basically, an atom is made up of protons and neutrons here in the center, in the nucleus, and then it's surrounded by electrons, and those electrons are in various energy levels. So we're going to say that this energy level has an energy of 2. 2 what? Well, I don't know. 2 energy stuffs. So this has 2 energy stuffs. This next level, we're going to say has 3 energy stuffs. And this next level has an energy of 8 energy stuffs. Now, I am totally making up these numbers. They don't mean anything. Don't go to your chemistry teacher and say, well, Kilo said that the first energy level has 2 energy stuffs, because they're going to look at you like you need to lower your medication a little bit, all right? We're just totally making these numbers up, because this is not a quantum mechanics class. It's not a chemistry class. We're not here to figure out exactly how much that energy is. We just want to say this has the least amount and a middle amount and a greater amount. And where these numbers came from, you'll see in a little bit. But again, I totally made these up. All right, so let's say that we have an electron down here in the lowest energy level. So it's got an energy of 2 energy stuffs. If we run some energy into it, and a lot of times we might run electricity through it, or it might be heated by something, then this electron then can jump up into a higher energy level. So when it's got extra energy, we say that it's in an excited state. And if you think about it, my daughter, when she was younger, she was a sugar-based life form. So if I give her a cookie, then she starts to bounce off the walls, because she's in an excited state, because she's got extra energy from that. Well, think about it. What is going to happen when she finally burns through that sugar? She's going to crash. And the same thing happens here. This electron can't stay in its excited state. It has to eventually drop down to its rest state, just like my daughter did whenever she crashed from that sugar high. So when this thing drops down to its rest state, then that energy has to go somewhere. And so it emits a photon of energy. And remember, we can call it a particle, a photon, or we can call it a wave. It's all the same basic thing. So whenever it drops down, it emits energy. That's the important thing. If it drops down, it emits energy, okay? So let's see what kinds of energy we can get. So let's say we're just pumping a whole bunch of electricity or whatever through one of these atoms here. So it jumps up, and let's say it jumps all the way up into this second shell, this 8th energy level, this energy of 8 shell here. So this is like giving my daughter 2 cookies. So now she's just seriously bouncing off the walls. Doing, 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 doing. Hi, Daddy. Doing, 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 doing. I love you. Doing, 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 doing. Right? And she's going to crash. As she burns through that energy then, she drops from 8 to 3. 8 minus 3 is 5, and so it emits a photon with energy 5. Now you guys know that the more energy it has, the bluer it's going to get. So this is quite a bit of energy, we were going to say. So we're going to say that it's a blue photon. Again, these numbers don't mean anything, just higher or lower energy. That's all we care about. Well, if she keeps going, she keeps bouncing off the walls, eventually she'll burn off some more energy. She'll drop from 3 to 2, and 3 minus 2 is 1. So she emits a photon of energy 1. Now, 1, remember, is less energy than 5, so it's going to be redder than that energy 5, right? So we're going to say that that's a red photon. We're going to say that's a blue photon. Now, another thing that could happen is, what if we give her 2 cookies, but then she gets in a tickle fight with her sister, and she burns through all that energy all at once. So she drops all the way from 8 down to 2. Well, now she's emitted 6 energy. So that's even higher energy than the blue, so we're going to say that that's purple. So if I were to project this on a screen, then I would get a red line, a blue line, and a purple line. Looks just like this. So this particular one happens to be hydrogen, but if I've got it, the rule is if I have a hot diffuse gas, diffuse means thin, means not dense. So if I've got a hot diffuse gas, then I'm going to get this emission spectrum that we call, because it's emitting these photons, and we only did the purple, the blue, and the red. But in an actual atom, there's a whole bunch of other electron levels that it could jump between and can produce a lot of different colors. This is that same type of spectrum that we saw before, but now if you think about it, instead of having our nice smooth curve, we don't have all the colors of light. We only have purple, blue, teal, and red. And this height here is still like a bar graph. It allows me to tell which one's brightest from all of that. Okay, so with a hot dense gas, then let's go all the way back up to here. With a hot dense gas or a hot dense object of any kind, I'm going to get all the colors, and so that's going to produce this continuous spectrum. But if I have a hot not dense, a diffuse gas, then I'm going to produce this. So what you need to remember with these, you need to remember the name of each kind of spectrum. You need to know how it's produced, a hot diffuse gas in this case. You need to know what it looks like. So an emission spectrum is black with colored lines on it, right? And then finally, you need to learn what it's used for. And in this case, we can use an emission spectrum as a fingerprint, because each element has its own set of energy levels, and it's not like any other element. So because those energy levels are going to be different, we're going to get different colored lines based upon the structure of the atom. So if I see a spectrum that looks like this, I know that I've got, in this case, hydrogen. Now it works the other way. Let's suppose that I've just got this atom sitting here, fat, dumb, and happy, hanging out. It's not getting any energy at all or anything like that. And I'm going to shine white light on it. Now remember, white light, which is produced by that continuous spectrum, so it's produced by a hot, dense object. It's got all the colors in it. And so red is, of course, the lowest energy, and purple is the highest energy. Again, these energy numbers don't mean anything. I'm just saying the energy is increasing as I go this way. All right, so let's say that that electron is just sitting down here in its rest state because it's chilling. It's just hanging out right here. So when this first red light comes through, when this first red photon comes through, the electron says, hey, I can eat that one, because 2 plus 1 is 3. And the important thing here, the only quantum mechanics that we're ever going to know, is that electron is either in the level 2 shell or the 3 shell or the 8 shell, and it is nowhere in between. It literally teleports. So it vanishes from 2 and appears in 3. And when it does that by just eating the energy. And if this photon isn't something that it can use, then it just passes on through. So when this energy level 1 comes in, the electron eats it, tasty, and all of a sudden it's up to energy 3. Now for the photon with energy 2, when it comes through, there's nothing for it to do. 2 plus 2 is not 3, 2 plus 2 is not 8, 2 plus 3 is not 8, so there's no way that it can eat that, so it just passes right on through. Now let's think about the 3. Is there any way that this atom can use this yellow photon, this energy 3 photon? Is 2 plus 3 3? Nah. Is 2 plus 3 8? Nah. Is 3 plus 3 8? Nah. So it goes sailing right on through. Now you do it with 4. Is it going to be able to use 4? Compare it to each of the energy levels and see if there's a way that it can use 4 to jump up into a level. Nope, 4 plus 2 is not 3, 4 plus 2 is not 8, 4 plus 3 is not 8, so it goes sailing right on through. Now, how about this energy 5? Is there a way that it can do it? Yeah, when the 5 comes in, the atom eats that photon and jumps up from 3 to 8. Tasty. And now that photon is gone. It's vanished from the universe. Now let's suppose that I've got a whole bunch of different atoms out here, but we're going to look at comparing from the ground state here, from the rest state. If I have this energy 6 photon, is there any way that it can be used? Right, so it can eat that and jump all the way up from 2 to 8, so it's gone. So what happens then when I project that on a screen is I get all of the colors. My camera went out there. I've got all of the colors except the 3 that got eaten. And so I'll have this rainbow just like I started out with over here, but I'll be missing color 1, which is red, color 2 here, color 5, energy 5 here, which was the blue, and then energy 6, which was the purple. All the rest of the colors will be there. So it's going to look like this. So you see that I've got all of the colors of the rainbow, but I'm missing just those colors that got eaten by the atom. So an absorption spectrum is when it absorbs the photon. To produce that, I have to have this hot, dense, glowing object. Remember, what kind of spectrum is that going to produce? That's going to be a continuous spectrum. So here's the rainbow. When that light shines through a cooler, lower density gas, just like we saw here, this is the cooler, lower density gas, then that gas eats the photons that it can use, only the ones that it likes. The rest of them, it just lets pass right on through. So there's only going to be a few that it likes. So that's producing this absorption spectrum. So an absorption spectrum is always a rainbow with black lines. And then if we look at it with our line spectrum, here's that curve, that rainbow that we're used to seeing, but now you see that there's some missing lines where it got absorbed. Okay? So continuous spectrum is produced by a hot, dense, glowing object. Looks like a rainbow. We can use that to get the temperature and the size of the object. The absorption spectrum, or the emission spectrum, the first one that we had, looks like black with colored lines. It's produced by a hot, diffuse gas, a hot, low density gas. And then we can use that to get the fingerprint of the atom, to identify the atom. Absorption spectrum is produced by a hot, dense, glowing object shining through this cooler, lower density, cooler, diffuse gas, and it looks like a rainbow with black lines. We can also use this to get the composition because these black lines are in exactly the same space as the colored lines were here. So the pattern is going to be exactly the same so that we can compare it this way. So if I have an object that is just a hot low density gas like a nebula, which we'll be talking about, that's going to produce an emission spectrum that looks like this. On the other hand, a star, the energy is produced actually in the core and it's hot and very dense. So what kind of spectrum is that going to produce? That's going to be your continuous spectrum. It's going to be the rainbow. So the rainbow here is being produced ultimately in the core. As that energy then goes out from the core, makes its way out, and then it gets absorbed by the cooler, lower density gas. It's still hot, but it's a heck of a lot cooler than it is on the core. So that absorbs these lines here. So it still enables us to determine what the star is made out of. So most stars then are going to produce this absorption spectrum. Most nebulae, hot nebulae, are going to produce this emission spectrum that we see here. So let's talk about how we can identify that. So let's practice. Look on your library here. Pause the video, take a look at this spectrum, and see if you can figure out what it is. So pause the video, do that now. Okay, so when we compare this, you're looking for the pattern of the lines, and you see that if I've got these two that are fairly close, and then I've got one here, and then I've got one off to the side here, well, the only one that matches then is hydrogen. So this is a hydrogen gas. So this is how we're able to tell that the sun is mostly hydrogen, because we see this emission spectrum when we look at stars. All right, let's try another one. So pause the video, see if you can figure out what this is. You got it? This is water. And so we can actually detect water on other planets if I can find it in its own particular, if I can find its particular spectrum here, because that's going to be unique to water. It's its fingerprint, its signature. All right, so that's it. You've got the basic idea. The practice is going to give you some more chances to identify the element. In the next lecture, we're going to first have to identify the element, then we're going to find those lines have shifted. We'll talk about that in just a second. So download the Finding Composition practice. Go ahead and work on that. Remember, you're going to want to keep this sheet available for when you're working with the rest of the class. So now you know how to find the composition of any object in space. And that's one of the more powerful tools of astronomy, because like I said, we can't go out and gather up that star stuff. If we want to figure out what the star's made, we've got to use the absorption or the emission spectrum, depending on what it's made of. Then, as I mentioned, sometimes though those lines will be shifted over from where they should be. The pattern will be the same, but it'll be shifted over. That amount of that shift is going to allow us to determine the velocity. So the first thing, before we can start working to figure out the velocity, the speed of the object, we first got to figure out how to identify the object. So it's really important that you understand how we're doing this composition, this detection of what the thing's made out of. So we'll see you next time.